Hey, everybody. Thank you all for joining us. We're going to go ahead and get started. My name is Jeff Druck, and I get to serve as the moderator for this session. Wanted to thank you all for joining us today for the Beyond ChatGPT Next Generation AI Technologies webinar. We're very happy that you're here. Earlier today, you hopefully got an email that had the disclosures and learning objectives, and that's also been posted in the chat. So if you want to look at that, please feel free. Also, our presenters are going to review that material shortly. This webinar will be recorded, and that recording will be posted on the web page for the SAEM website for future people to view, so that way we're creating an enduring academic material. Throughout the session, please post any questions that you have for the presenters in the Zoom chat. There'll be time at the end for the answers to these questions, I'm going to be collecting those, and so you can put them in the chat whenever you like. They will all be given to the presenters once we get done with the initial presentation, so that way they can answer everything at the same time. And if you could please turn off your audio and keep it on mute unless you're actually speaking, we would greatly appreciate it. Okay, with that being said, thank you again for joining us today. And I have the pleasure of introducing your panelists. It's Carl Pritchitz and Christian Rose, both from Stanford, Andrew Taylor from UVA, and Moira Smith from UVA. And lastly is Josh Joseph, who's at Brigham and Women's and is unable to attend today because he had a baby today. So I think that's a pretty good excuse. With that being said, I think, Carl, you get to start us off. Is that right?
Yeah, you can. Christian's going to start. How's it going? I'm Christian. This is Carl. We had the opportunity to co-present from the same room, so we decided to do that. None of the members have any formal disclosures other than Dr. Andrew Taylor here, who has grant and research opportunities from Beckman Coulter, which has subsequently ended, and Vera Health as an advisor. Again, there's a link to the disclosures and things in the chat. The learning objectives for today are that upon completion of this webinar, we hope that you'd be able to implement AI technologies and use them to enhance decision making in your clinical practice, or use them for research and teaching. This is beyond ChatGPT, so maybe you'll be able to actively implement them. There are things that can happen just on your cell phone, but also you'll learn some techniques you might be able to use to engage with these technologies specific to your local needs. Next slide. So, why are we talking about this right now? Obviously, many people on this call and at SAM earlier in the year are aware that emergency medicine, continues to see the strain of increased patient visits, increased patient complexity, more boarding, staffing shortages, all of the, amazing things that our peers are trying to, all of the little fires that our peers are trying to put out all the time. And because of that strain on the system, it's left a lot of people wondering, well, how do we meet the supply demand mismatch and gap that's going on in emergency departments across the country, which is where, AI comes in as a possible solution. Next slide. There's been a huge uptick in the number of articles referencing AI in our field, obviously, whether it's in triage or discharge or monitoring people at home. People are using artificial intelligence in many new and varying ways to try to accomplish the many goals of, unplanned care in the urgent and emergent settings. Next slide. So we know it all started with ChatGPT, and I'm sure most people on this call have used it or interacted with it in some level at some point, whether in the last month or over the course of the year. They have about 700 million active weekly users, it sounds like, which is very impressive from a technology that was only introduced a couple of years ago. But we're going to go a little bit beyond the ways some of you have been using ChatGPT to talk about what's coming next. But we're also aware that this field changes very rapidly and quickly, and they even just announced GPT-5, in the past week, and all the new capabilities therein. So this will always be a moving target and change as we go. So we hope you, stay tuned and get involved with more SAM stuff to keep up to date and keep progressing as the field changes. Next slide. So the topics that are beyond the regular ChatGPT sort of question and answer sessions are going to be on the left, we're going to talk about retrieval augmentation. We're going to talk about agents, multimodal AI, and then thinking models and what those mean and how to utilize them in your practice. Next slide. As we mentioned, I'm taking over for the amazing Dr. Josh Joseph, who introduced a new member of his family. So if I stumble on any of these slides, I apologize. The I will just blame Josh as the new dad. He's gonna, get more blame anyway. So I'll take it from there. So next slide. So the first thing to know is this prompt here might remind you of the early days of your use of ChatGPT, where prompts are generally limited by the context knowledge of the large language model. So say you're as a user like, can you tell me the ICU admission policy for hyponatremia at the Yale New Haven Hospital? If I really wanted to know this, I probably would message Dr. Andrew Taylor or one of the Yale colleagues who knew the answer, but you might, go put it into ChatGPT and look for an answer. Next slide. The problem was in early models of this that I don't know if you guys all remember, if you asked it for current events, it would say, I'm sorry, my last update was January 2022, and the TLDR of all this is I don't know that I was trained on the contextual knowledge of the ICU hyponatremia guide. Here's some things I think about based on all of the training that this LLM had in the first place. So it's taking all of the training data and searching for an answer based on how the LLM was trained at large, which could be the entirety of the internet, but also could be a couple of years old and might not be relevant to your specific question or your specific location. So next slide. So what do we do with that? I'm sure if some of you have used ChatGPT more recently or Perplexity or things like that, you might ask the same question again. Can you explain the policy for ICU admissions and hyponatremia? And next slide. Your answer nowadays might be a little bit more directed towards local knowledge and website use and additional information that has been retrieved by the LLM that's up to date. So the way it works and the way it interprets your question was all done by the training early on. And then it tries to get new information from the internet, but has to be told where to do that. So we're going to go over a little bit of how that happens. Next slide. So how do we add that context? As the question we're going to try to answer right here. Next slide. This is the process of retrieval augmented generation. The generation part is generating your answer. And then we have this retrieval augmentation system where we're going to go to for that up-to-date information. We're going to go through each of the processes in this over the next couple of slides. So next slide. The first thing is that you have to, add a knowledge base. So if you're going to try to augment your information retrieval and generation, the first thing you have to do is tell it what to use for that information. So you could have an old LLM trained on, old data, but maybe for you, you're like, oh, our hospital, this is the case at Stanford, we have a whole admission guide and admission grid. We have processes for the CDU. We have schedules, who's on call. All this information is updated, frequently and, can be changed monthly or daily, and we need people to be able to find answers across that. So next slide. So we're going to try to, give the retrieval augmentation system that information that we want to use to find more accurate answers. So the first thing we do is, okay, go collate, get all the documents we need. Next slide. Well, then we have to be able to make it usable to the LLM. So you might think, oh, I'll just send every single document in there, throw it into the LLM, and hopefully it'll search through there and give me an answer. It turns out if you want to actually create a retrieval augmentation system, you're going to need to break down each piece of information into a retrievable context. So next slide, you'll send that information into a chunking mechanism, which will basically first break down the many documents you have. You could have, a Shakespeare compendium's worth of information just for your local ED processes. And the first thing is that you don't have enough tokens to put that whole thing in. I'm sure some people have tried to put PDFs in. Sometimes people are using, GPT for a, at-home journal club, and you've been told, oh, you don't have enough tokens for this. You should break it down. So the first thing it does is make the size more manageable to the models and to the system. The other thing it does is allow you to sort of hone in on individual pieces of information that are relevant when you subsequently ask a question. So if you have all of the details of every process in the ED in one long run-on sentence to the machine, it kind of doesn't really know how closely related each piece is. So you have to chunk it into different sections and give those back to the retrieval system. Next slide. Once you have those chunks of information, this is where we're getting into almost like, in my mind, the LLM within the LLM, which is that we're going to code with embeddings each of those chunks into a multidimensional space. Maybe one of those chunks is about CDU admissions. Great, those are going to get put into one sort of area. And so chest pain going to the CDU might look different than chest pain needing admission. And so those will exist in different space, and that's based on the embeddings, which are essentially the way that the LLM knows how to find information. Next slide. This is just an example again of the embeddings for different topics get different locations in this multidimensional space. And so each of those processes are going to get broken down in that way, get given different vector locations that will then determine how closely related they are to one another. Next slide. And then we give back to the retrieval augmentation system the vector database, all the different dimensions, where all of those chunks exist. And now it's got this system that it can use to go find more detailed specific information. Next slide. All right, so now we've set up the system so we can, use information that we have locally. The next part is like, how do we actually retrieve that information? So next slide. Say you're the user and you ask, then, yeah, I have a patient with, low risk chest pain who I want to send to the CDU at Stanford. What do I do? Or maybe it's the ICU hyponatremia policy. You ask the question. Next slide. That query is then sent to an embedding function. That question is then broken down. So from the first graph, we had what did the president say about Justice Breyer? That might be recent topical knowledge that the LLM has to retrieve from your augmented system. And it's then going to break down your question into what it thinks is the right, vector for the question to say, oh, we're talking about, for us, CDU again. We're talking about CDU and chest pain. CDU chest pain and what, orders to place, say. Great. So now we'll understand what the question is and we can go look for the right answer. Next slide. So that gives us essentially, how are we going to use those embeddings to answer this question from our local system? Next slide. I loved this. I did not get this image myself, but I thought this was pretty good of like, where on a graph different types of music would be. But that's essentially what we're talking about. So you have Peter, Paul, and Mary up in one quadrant, and then you have the query of like thrash rock should get you Metallica, Slayer, Anthrax. It should be in a different portion of space, and all of those bands should be really like close to each other in that multidimensional space, and maybe not really near, the Eagles or the Grateful Dead. And then we're going to go find what the answers are from those embeddings. Next slide. And this is just what they might, again, look like. They're returned to that space, and those answers are returned from the RAG system to the LLM to then give us their answer. So next slide. All right. We've gone through, given information, search through our local database and our multidimensional space for an answer. And now we're going to try to give the person querying the system the actual answer. So they go into the LLM, the large language model itself, GPT, Claude, whatever it is. They put in the question. The question's broken down into the local knowledge base. The local knowledge base then will give a version of the answer that's augmenting what the LLM was going to respond in the first place. You can go to the next slide. So it has a first prompt and then it's augmented by the local knowledge, which is in this case, oh, what did the president say about Justice Breyer today? Oh, in the news I found from this webpage, here's what happened. I'm going to give that to the retrieval system and back to the LLM. So next slide. Ultimately, that then generates the LLM now interprets the information from the RAG system, interprets the question, and now is trying to give you an answer back using only the local knowledge, but still now needs to interpret all of those different vectors before giving you the answer straight up. And then it comes back with the president thanked Justice Breyer for his service and acknowledged his dedication to saving the country, etc. And all's well. It didn't make up the big important things to think about here is it didn't make up information. It didn't just confabulate. It looked for information in the places we told it. So that gives you a lot more control over local question and answer. Local like question answer integrity avoids some of the hallucinations because now instead of a huge, all of the potential space of the internet of knowledge, it's working only with your local information and gets you what you need. Next slide. And some of the applications for this are chatbots for policies and procedures like we talked about. But the next thing that's coming live in several systems is summarization of EHR notes. You can imagine the RAG system there is all of the notes on different patients and encounters broken down into little snippets that you can then search when you're reviewing one patient's recent, hospitalizations or outpatient. Or you can ask questions of the EHR notes, what was done recently for this patient by their outpatient doctor. And it will only use the retrieval augmentation system of all the more recent information that was shared with it. Next slide. We're at the end. For us, just wanted to share that at Stanford, we've recently gone live with something called Chatter, which is a platform to allow us to start retrieving information from live notes. And if you have questions about that, check out some of the releases or email us to ask more questions. And we can go on to the agentic workflows next. I'll pass it off to Dr. Taylor.
Cool. Thank you, Christian. And we can go to the next slide. Okay, so we're going to shift gears just a little bit and talk about AI agentic workflows and our AI agents. You can go to the next slide. So, you may be wondering what an AI agent is. I would say I think when we initially designed these lectures is about a year ago, and probably very few people had heard about AI agents, and it's just amazing how fast things are moving, because now I think they're largely mainstream. You've probably, if you're using ChatGPT, probably experienced this now with some of the new functionality around this, where you can go in and there's an agent function within ChatGPT. And you can ask goals and questions about like I'm looking for a flight to Miami. Can you figure out what times and everything else? And it will go and search on the web and be able to break down things, probably give you a table or something like that. And so it's a very different type of AI kind of system than we've probably been used to in the past, where you're really giving it goals and asking the AI system to really pursue those mostly autonomously. And that's a key part about this, is that it runs really just on its own with really limited direct human supervision. Next slide. So this is just kind of a comparative slide between the kind of old traditional AI models and thinking about AI agents. And so from a traditional model, usually the way that these are kind of built out is you can think about, you have some classification task where you want to predict out, whether somebody's going to return to the emergency department in 72 hours. And so that you have this kind of binary outcome, and, build out the data set and apply a machine learning tool on top, and you train it out. And it's a very specific task. It's very confined to kind of the initial kind of input and what the user had really defined around kind of the whole setup for that. And it's going to give a very kind of defined output from that. AI agents are very different. So they're dynamic, they're autonomous systems. As I mentioned before, they really are designed to pursue goals over multiple steps. And a lot of them, and I think Carl will probably talk about this in the reasoning aspect of things, a lot of them will break these tasks down into multiple steps and multiple goals underneath. So, let's say I tell it I want to build a website, and it can definitely do these things now. If you are using things like Cursor, you can easily build websites, apps within hours now. It's pretty crazy. But, if you watch it work, what it does is it'll take that kind of complex goal of building a particular website, and then it'll break it down into smaller goals. Okay, I need to build the back end of the website. I need to build the front end aspect of things. And for the back end, I'm going to need this particular type of database system, and so on and so forth. And then the next thing that it will do within this is it perceives its environment and will take action. So as it's, most of these are writing a lot of code. As it's writing the code, if it encounters some particular error, it's able to recognize that error. It will then make adjustments to the code, go back and kind of rewrite the code, rerun everything from that, and make sure that things are working, and then move forward after that. The other thing I think, and this really gets into the kind of workflow and a kind of agentic aspect of this, is kind of the interaction with other AI agents. There's been some really notable things that have come out in the press around, like, even kind of a full lab that's just composed of AI agents. There was some work in, I think, in the chemistry or biochemistry domain, where a group of agents that were serving different functions. So one was the statistician, one was an ethicist, one was something else and something else. We're all working together for a particular task, and we're able to kind of generate some novel insights from in that kind of biochemistry domain. Next slide, please. So these are just some of the kind of critical capabilities of these agents. So I had mentioned the aspect of autonomy. So really, the real power of these is just letting them go and doing their thing without a lot of human intervention. So that's that autonomy aspect. And that raises a lot of questions around ethics, and that's a whole nother area to talk about sometime in the future. So they have this reasoning capability. They're able to take, contextual information to make judgment calls, to weigh trade-offs, and Carl will again talk a little bit more about that. They have adaptive planning, so they're making dynamic adjustments to their goals and plans. If it runs into an issue and it can't, a lot of times when I see is like if it's programming something and it runs into an issue, it'll start to look for go arounds and trying to figure out a different way or a different kind of pathway to be able to accomplish the goals. So it has that aspect of things. It's communicating, most of this stuff in kind of just natural language, and that's the way it's, talking to itself and it's talking back to the end user. And, I think as we see more of these come into existence, a lot of it is going to be focused around workflow optimization, moving between subtasks, trying to do this efficiently, because you can think about how the, amount of resources that could be potentially used by these AI agents as we move forward. Next slide. So, why is kind of agentic workflow really kind of the future? So if you think about like conventional AI, you have this programming around really individual repetitive task. I kind of mentioned that traditional aspect of it, defining a, particular kind of end goal outcome. But there's, this suggestion that multiple, agents can really help encourage like this kind of divergent thinking aspect to really improve factuality and reasoning. You could think about having one agent that's actually reviewing another agent's output within that. And a lot of kind of the existing models that you're now seeing, even if on the surface it looks like one agent, a lot of them are running multiple agents underneath the systems, and they can provide aspects like validation moving forward. Next slide, please. So this just gives you a kind of an example of the performance enhancement that you get from using kind of agent workflows. So this is kind of an evaluation metric. It's called human eval, and it tests the general performance of these generative AI aspects. And this is a little bit older now because it's just GPT 3.5 and 4. But what it's showing you is if you have zero-shot learning, so you're not providing any context, you're not providing really any kind of additional information. The performance on this question answering aspect, for GPT 3.5 was around 50%, and GPT 4 is moving up in the 65 kind of range. But if you start to build out these with tools and agents where they're able to go grab context, they're able to talk to each other and so on and so forth, and you start getting significant performance enhancements after that. And so that's why there's been this general movement towards using agents in a lot of different environments. Next slide. So just some of the workflows that you'll see with these, there's this reflection component where it'll kind of examine its own work, just a lot of times like the way we would kind of work through things. A big component about this and moving forward is going to be in tool use. You may have heard things like model context protocols, but basically you can think about it like where a lot of the best one example I could give is like, okay, you have your clinical decision rules. So you have your heart score, you have your Canadian CT score. Those are all potential tools that could be used by an AI agent, and so they can go out and grab that tool and apply that tool to a particular case. And that's how a lot of these are going to be functioning moving forward. We've talked about the planning aspect where you have this kind of multiple step process and it's looking for kind of execution or is it getting towards a particular goal. And then the multi-agent collaboration piece of this is really going to be critical, I think, as we get to more complex tasks moving forward. Next slide. So these are just kind of particular organizations that you can have when you move to that multi-agent aspect of things. You can have multi-agent conversations. You can have them in different kind of hierarchical patterns. The healthcare context I would give around this would be like, you could have a single agent that is working on improving diabetes for care for patients. So, its goal is, to improve diabetes. It may do things like, look at the patient's prior, whether they have a hyperglycemia, manage their medication aspects of things, make recommendations, and so on and so forth. But that's just one agent. You can think about, deploying multiple agents that all have different goals and tasks within the system, and then you need some type of kind of organizational structure that manages all of those agents within a system overall. Next slide. So, where could AI agents kind of fit within the emergency department? I think this is going to be really along the continuum of care. You can think about it from a triage aspect of thing, having some kind of intake agent that's there. You could think about it from a diagnostic support agent that may actually, communicate with the triage agent. You could have one for ED coordination overall, disposition planning, and so on and so forth. And I think we're going to see these moving forward in the next couple of years. This is definitely where a lot of kind of business has moved. You've probably seen them if you're starting to use tools like a lot of like website design and things like that are starting to use a lot of these tools. But some collaborative aspect with agents, we will interact with them moving forward as well. Next slide. Good. And I think that is it. I will turn it over to Mara. We'll keep going.
Thanks, Andrew. So many models are unimodal, meaning they are processing one type of data at a time, and most commonly this is textual data. In reality, healthcare, and in particular emergency medicine, is inherently multimodal. So we make decisions in the emergency department by integrating very diverse streams of information. This includes clinical notes, it includes imaging studies, lab results, ECGs, physical exam findings, patient-reported symptoms, and past medical history. So multimodal AI represents kind of the next leap forward. AI systems that can simultaneously process and reason across multiple different data types to generate richer, more comprehensive insights. And this shift is important because it more closely mirrors human clinical reasoning, where we don't silo information by type. It also allows for AI-driven tools that can interpret context across multiple sources, hopefully leading to better decision support. And it creates opportunities for applications that were kind of previously out of reach for purely text-based AI that we will get to a little bit later in this presentation. Next slide, please. So multimodal AI. When we're talking about multimodal AI, we're referring to systems that can process and integrate different types of input. So for instance, textual images, text, audio, visual, video clips, other data streams all at once. So think of this as breaking down silos between data formats. So in the ED, this can mean combining data from EKGs, chest x-rays, nursing notes, lab values, bedside ultrasound clips into a single reasoning process. So instead of having to separate systems for each type of data, multimodal AI can, sort of quote, see the whole picture in a way that's much closer to how we think as clinicians. Next slide. So in essence, a multimodal AI is trying to have a means of having more complex, richer inputs to generate more comprehensive output. Next slide, please. So where are we seeing multimodal AIs currently outside of healthcare? So self-driving cars, integrating a lot of different data streams, spatial data, visual data, input from both inside the vehicle and outside the vehicle. In the agricultural world, we're seeing multimodal AI from sort of crop rotations, taking data into account from climate, soil changes to kind of generate data based on crop rotation and enhance agricultural output. Social media, obviously, social media takes into account both text, photos, video clips, voiceovers, music to generate, the kind of social media content that we're all familiar with. In retail and the retail space, multimodal AI is being used to generate demand forecasting and to sort of, be able to predict inventory using RFIDs, shelf cameras, seasonal trends, holidays, even weather patterns. In manufacturing, it's being used for not just predicting, how many dishwashers need to be produced each month, and in which facilities, which areas of the country, but also anticipating maintenance needs for products as well. Energy, same scenarios, taking into account natural disasters, seasonal patterns, temperature fluctuations, and again, holiday special events, those sort of things. And then language apps like Duolingo, using various different types of data, voiceover, video clips, text, pictures, to have a more robust learning experience. Next slide, please. So now let's bring some of this back into the emergency department. We routinely have multimodal data at our fingertips. This includes EKGs, point of care tests, ultrasounds, clinical records, imaging studies like CTs and chest x-rays, vital signs. And synthesizing all of this data is a challenge, especially to do it under time constraints and competing priorities in the emergency department when taking care of multiple critical patients at once. And the key here is not just processing these different data streams, but integrating them into coherent, actionable outputs. Next slide. So what does this matter for us? Why should an emergency physician care? So first, hopefully more accurate clinical decision support. So the idea here is that if you have richer inputs, there is more context for an AI model to make a recommendation, and hopefully that can translate into safer, faster care. So models that combine imaging studies, clinical notes, vitals, hopefully would be outperforming models that just look at one type data. Secondly, real-world complexity. So emergency department patients are often undifferentiated and complex, and multimodal models more closely mimic how physicians synthesize, for instance, chest x-rays, ECGs, troponins, physical exam findings simultaneously. There's also what we're trying to get to is potential future tools. So think of these, the potential for, triage tools that can do more dynamic risk stratification, more nuanced diagnostic support for conditions like sepsis, trauma, stroke, and even, trying to predict disposition decisions. So, for example, trying to predict which patients are going to need admission and predict inpatient bed needs. And then, some of these models are already being integrated into ED workflows, and some of them directly into the EHR, some of them kind of working in conjunction with EHR tools. So one example could be an AI, model that suggests a PE workup pathway, after kind of initially reviewing initial vitals and, prior clinical notes. And then one sort of big caveat here is that these models are not without equity and bias risks. So multimodal models might unintentionally amplify biases that are already present in different modalities, and that can sort of take biases or patient populations that may be over or underrepresented in data sets and actually enhance these biases, which makes it very important for us to make sure that we are training models on as diverse and representative data sets as possible. Next slide, please. So current applications in emergency medicine, we're still very early in adoption, but there are models that are being used and being tested now, including ECG interpretation, not only just to try to do early identification of early myocardial infarction, but also doing things like reducing the the noise, the artifact in ECGs, and combining ECG data with data from a patient's wearable, such as an Apple Watch. There is multimodal sepsis detection tools, some that have been built outside of the EHR, some that have been built into the EHR, such as Epic's sepsis prediction model. And these combine data like vital signs, labs, the goal being to identify sepsis earlier than when the clinician does. So far, I think that all the clinicians are still, for most of these models, still identifying sepsis either earlier or at the same time than the models are, but that's the goal of the sepsis models. Another big area that's currently being studied in emergency medicine is triage. So AI-assisted triage that's incorporating, patient's chief complaint, initial intake vitals, sometimes even audio recordings of what the patient says on their initial intake and registration. And so several, potential implications of this. So, can we predict who's going to need a hospital bed, who's going to need admission, with the goal of trying to potentially reduce boarding times in the ED if we can identify early on who's going to need an inpatient bed. Critical care prediction, trying to identify early on who's going to eventually need intensive care or other higher acuity services. And in general, improving triage accuracy. So we all have a lot of level 3s that present, and we're working on having triage models that more accurately sort of bucket these out into more 2s and 4s appropriately. And there's also a lot of pre-hospital triage models to take this even before patient arrives into the emergency department. And so in summary, multimodal AI brings together multiple data types to do in real time what we're doing in the ED every day, which is real-time clinical reasoning. And speaking of reasoning, I'll hand it over for our next section on reasoning models.
Awesome. Thank you so much, Moira. All right, the last section we're going to talk about is reasoning models, and these are models that will integrate some sort of a thinking process to give you better answers. There was a lot of excitement or angst. I guess it was several months ago now when DeepSeek unveiled some of their first models that integrated some of these properties and got high levels of performance with comparatively less infrastructure and less training requirements. And similarly, since then, there's been a major development of a number of different reasoning models. So let's talk about how these work. Next slide. All right, people can't shout out here, but Christian, what's this?
I'm worried about STEMI right now.
Great. Yeah, you see this
Or no, am
EKG.
I?
Yeah, you see this EKG, you think of STEMI. So next slide. What this is called, and I have an education background, this is your system 1 thinking. So that's sort of your immediate pattern recognition. What do you think is going on? What are your impulses? What is your immediate answer? And a lot of original LLMs and a lot of the LLMs that don't use thinking processes are system 1 thinking. They will start to come up with an answer immediately without any reflection, and sometimes that answer can be erroneous. As many of us know, when you've immediately thought something is going on, and then you take a closer look and realize that actually your initial impression was wrong. Next slide. All right, here's something else. What can you interpret this acid-base scenario for me?
That's what's going on here. I mean, I have to do some summing, but maybe looks like not acidotic, but maybe there's a gap. Vomiting. Yeah, where else do you want me out there?
You can go to the next slide. Next slide. So hopefully this slide gives people flashbacks to medical school with a blue background, but this is a mixed disorder. And, doing acid-base calculations, that's an example of system 2 thinking. You can go to the next slide. That is sort of the slow, deliberate reflection where you need to slow down and say, something doesn't fit my pattern. I need to be careful and think a little bit more deeply so I don't make any mistakes. And basically, this is the principle that's integrated into these thinking models through a variety of different processes. They go through periods of reflection where in some of the models, you can actually see these what are called chains of thought, where the model is sort of doing this internal monologue and reflecting, which looks very analogous to what I think is going on in my head when I work on a complex problem. It'll say, here, I think this is the answer. Oh, wait, that might be wrong. Let me think a little bit more about that. And you can actually see the model going through these processes of reflection in order to come up with a more accurate answer. You can go to the next slide. So I wanted to put some of these models to the test, just as an example. So I thought, here's like a cognitive challenge for one of these thinking models. Here's the New York Times crossword. This is a Saturday, and if you do the crossword at all, you know that Saturday is the most challenging. And I really wanted to put this to the test. So I gave this, you can go to the next slide. I gave this to one of the I think this was GPT-4o, which was one of the advanced models that doesn't incorporate thinking at the time. And you can go to the next slide. I said, solve this for me. And it said intellectual was the first one across. And you can see that intellectual is not a 9-letter word. So right off the bat, it's sort of shot from the hip, and its initial thought was erroneous. And it didn't really have that process of reflection to see, like, actually intellectual is not a 9-letter word. It won't fit in here. You can go to the next slide. So when we did this before, one of the more advanced thinking models, OpenAI's O3, I gave this to that model, and I wanted to see if it could reflect and think about the process. But it was actually a little bit too smart here because it realized that this was a New York Times crossword recently, and it said I could probably find the solution online for this. And it went and searched and found the solution. I did give this to another model without access to the internet, and it struggled with it and didn't quite get there. But you can see that, obviously this is thinking a little bit smarter. It reflected and said, rather than just guessing at the answers, why don't I look for the answers on the internet and come up with a more accurate solution? Next slide. So taking another example of how this might play out clinically in terms of getting better results, here's a very complicated case presentation that I came up with. It's somebody who presented with shortness of breath. They've got a complex past medical history, and they come into the ED, they're very sick, they're on oxygen, and there's lots of lab information to interpret and sort of figure out what's going on with this. You can go to the next slide. If I gave this to GPT-4, which again was a non-thinking model, but pretty advanced in terms of its abilities, it came up with a differential diagnosis, PE, pneumonia, exacerbation of asthma. Keep going to the next slide. Came up with some investigations that we could do in the ED, and then next slide. And some disposition planning. But this, as you can sort of look through here, it's pretty surface level thinking and doesn't really go into some of the complexities of this case. And you can see that this is sort of the immediate answer that a model that didn't think very long would come up with. But if you give this to a thinking model, and you can go to the next slide, this is an O3 response, which you can see there's a lot more reflection here. So it gives a rapid clinical impression that sort of synthesized a lot of the data. It gives you a ranked differential diagnosis with factors that support and things that argue against it. It actually computed a Wells score and then also recommends sort of empiric coverage for community-acquired pneumonia. You can go to the next slide. Goes through and comes up with ED investigations to order immediately, and keep going. Immediate airway management. And you can see that this just reflects a lot deeper processes in terms of thinking about what the appropriate answers are and actually considering the complexities of the situation rather than providing an immediate response and a fairly naive answer. You can go to the next slide. It's even gone through sort of some interpretation of some results and then what you would do in that, thinking sort of longitudinally and thinking about all these potential different scenarios. And that's really what you get out of these models. They pursue different lines of thinking and then reflect and amalgamate the results to give you a much more in-depth answer. You can continue. And unlikely to be safely discharged. I agree with that. And then you can go to the last slide. And it goes through, it really hits very well the diagnostic complexity. So you can see that process of really allowing a model to think for a longer period of time and expand these chains of thought really will give you a much more in-depth answer. Now, this, to things that Andrew's talked about and Moira's talked about and Christian's talked about, that now part of the problem right now is determining, well, what's appropriate. Some things we need a rapid answer. Sometimes we need like a short response, and maybe this long thinking process like this can take up to several minutes to come up with an answer. For some situations in healthcare, perhaps that's not necessary. So right now, a lot of the discussion is determining how do we appropriately titrate the needs to the question we're asking. Do we need to do this system two thinking and navigate all this complexity? Or is a system one response, perhaps with augmented information through a RAG pipeline, maybe that's sufficient to get accurate answers? And that's something that a lot of AI labs and a lot of the field is working on right now to try to figure out, well, how do we titrate to the question? How do we get the appropriate level of compute that needs to be required? You can go to the next slide. And so that's the summarization. That was a short overview of thinking models. And what we've gone through today is a coverage of sort of these add-ons to ChatGPT, the things that are beyond just large language model in the original development, and talking about how things have been added on top of them to bring us to sort of the current iteration of large language models. Even since the time that we gave this talk a couple of months ago at SAEM, there's been more developments and more things. As we all know, this is a rapidly growing field, but these are some of the base ideas that have really been incorporated and really have improved the accuracy of the models and their usefulness for a lot of more complicated applications like things in healthcare and the clinical environment. So Christian talked about retrieval augmented generation. Andrew talked about agentic systems, which there's still a lot of excitement surrounding that and many more applications I think we're seeing every day. Moyer talked about multimodal applications, which, again, has important implications for being able to communicate with these models with different ways and providing them with different forms of information. And then I just covered some of these reasoning models that really go through the same process, but allow the models some time to provide reflection and really minimize the risks of hallucinations and inaccuracies in some of the responses. Next slide. I think that's all we have for everybody today. Thank you for being here. We answered some questions in the chat, but we'd happy to take other questions.
Yeah, thanks, guys. Hey, everybody, this was a wonderful presentation, and I really appreciate it. I know that you answered some of the questions in the chat, but I was hoping you might be able to elaborate a little bit if you're okay with that. The first question was from Steve Epstein, which was, for summarization, what are some methods for adjudicating between the voluminous intern node and the pithy but more highly relevant consultant node? And this, I think, was speaking specifically about the node evaluation model that is being implemented at Stanford. Is that right?
It could have been. I will find out. I mean, it's hard to say. In and of itself, there was even just a recent study by Ziad Obermeyer, an EM physician who's at Berkeley and in Nature Communications, I think, about predicting, provider sort of burnout level and their ability to make decisions based on what their note content looked like and the use of certain words or the undulation in terms, how long the sentences are, etc. So if you're taking all the information that goes into the system, like chatter, say, and you have, yeah, student notes and attending notes and everything, you can obviously label and know who those notes are written by, and you could choose to hierarchically access some information and not others, but that's not really realistic at the scale we're talking about. At the same time, it sort of can determine, is there, lots of evidence, there's the vector such that there's lots of evidence from many notes that this person has, could be chart lore of a certain condition, but for the most part, it seems to have some inertia and gravity and truth, as opposed to one-time mention of one thing in one note as a side, a side area. These systems are able to sort of determine the gravity around medical concepts and what's been said within the notes. I don't know that it can, specifically say like, oh, it's going to sort through the really long, intern note versus the, couple of line attending one and give better weights to them. That's for us to choose. But you also, once these come to you or the summarization comes to you, a lot of the retrieval augmented generation systems will allow you to drill down or click where that evidence came from. So you could also go back and see the provenance of that information and decide for yourself whether you agree with it. Just like when the intern tells you something that you may or may not believe that they were told by the patient.
Also, I mean, in terms of the architecture of a retrieval augmented generation system, the rudimentary basis of it is retrieving notes from a vector space or information from a vector space. And that is based on a simple similarity of vector search to try to find similar information. That is the most naive way of doing that. There are additional things that you can add to that pipeline to improve the quality of things that you get. So, for example, some of those systems there's initially a vector search that is very fast and easy to run across millions of different documents. And then sometimes there will be an intermediary large language model called a re-ranker that will actually look through those responses and say, these are the ones that actually fit better. These are the ones that are going to be more useful for making clinical decisions. And these are the ones that are going to be less useful. So there are different ways to do it within the pipeline. And then a lot of the way models are trained in terms of giving you quality feedback are they take reinforcement and they take feedback from physicians. So physicians or users. So they're some of these technologies that are rolled out, like Chatter, I believe, has a method for providing feedback and say, this is a good response, this is a bad response. And the model will learn and apply different weighting to the information that it retrieves in order to learn these, the intern notes are not going to be high yield and the attending notes are going to be high yield, or, it's probably more complicated and nuanced than that, but learn what information is going to be most useful for making clinical decisions. And that's going to get iteratively better as the models get more feedback and more people are using these.
Thank you both. The next question was Andrew McFadden, who asked, have you seen any AI providing actual clinical decision support information, and how helpful, accurate has it been? And I know that Carl and Kristen, you put a study that you had done in the chat, and then Andrew also put a study in their chat. If you could just provide a brief summary of those two elements and what exactly it is that the clinical decision support provided and how it was helpful.
I think I'll give a very generic, I guess, response to all of this. So there are definitely instances of AI systems that are currently in place that are, making some improvements in healthcare. And, there's stuff around like diagnosis, there's stuff around triage, there's stuff around dispositional stuff. There's a lot of things in the deterioration space that have shown, some improvement in outcomes. So they do exist. I think the disconnect you're really seeing right now is that the EHR systems that we have currently are really not capable of doing the implementation that you're seeing from these tools and stuff like that. We do not have the ability to be able to massively run large language like GPT-5 and just let it go and touch every piece of data within the system and provide all of its knowledge back to the provider. Now, if it did, I think we would see huge performance differences from that. And there was another comment, I think, later on too about the FDA space. I honestly think the FDA ballgame is over. I don't think my general opinion is that we're going to be moving away from FDA approval for these products because we're in a space now where almost all of these tools are not single application tools, and we're going to see greater and greater expanse. And it's going to be like you're going to approve one AI system for the healthcare like entity and enterprise in the future, and then that's going to be it. That's where we're seeing consolidation. So I don't know if we're going to be in this kind of one-off model scenario, very long into the future afterwards.
I think the other question that sort of comes up with the last two questions on the chat were talking about how comfortable we are with the models being hallucination and bias free, and again that whole idea of how much you trust them versus how much they leave something else out.
Yeah, and that's I think where Christian's part of the talk with the RAG stuff is super helpful. So now, to really ensure trust within them, a lot of the RAG systems are bringing that piece of information back and then providing the citation or the link, the direct connection to the piece of data that's going into the response. So that's really designed to create trust within the system. And then my last plug on this would be like, we can't expect these systems to be 100% perfect. The comparison has to be against humans in the real, in real time and looking at, different outcome components. Because I don't think we'll ever get perfect within the systems, but I do think they're going to be far better than us at being able to search through mounds and mounds of data to be able to make recommendations moving forward.
Yeah, I think that last point is important too. And I think part of this
I
is
know we're
making us aware of some of the limitations that exist currently in the clinical environment. Like patients are not hallucination free, and a lot of the lab testing we do and a lot of recommendations and things that we incorporate into our clinical practice are not free of bias. We know there's problems with bias in a lot of the literature that guides a lot of management decisions. So the expectation for it to be 100% bias free and 100% hallucination free, I think is unrealistic. Probably better is understanding that those limitations exist in a variety of different instances, not just AI instances in the clinical environment. And then how do we still make accurate clinical decisions that are the best for our patients with the data that we have at hand? I mean, I'm sure I hallucinate and misremember data and management decisions all the time when I'm working. And, thankfully I work with some smart residents that point that out for me. But humans are not unbiased or hallucination free either. So I think being aware of the limitations everywhere, not just in AI tools. And honestly, I think the hallucination rates and accuracy are probably less than a lot of things we currently encounter.
Thanks, everyone. We're at time, and I want us to be able to wrap it up, but I wanted to give Moira the chance to sort of give us a final summary and wrap up.
Yeah, thank you. Thank you so much. So, I think what we've heard is a lot of augmentation and next steps for where the future of AI is going. And I will say, if you all are interested in this, all of us are leaders in the SAEM Informatics, Data Science, and AI interest group, and we would love to have you if you're not already part of our group. Please go to the SAEM community site and sign up. We have monthly meetings and webinars, didactics at the annual meeting, and would absolutely love to have you all as part of our group for continued discussion.
Thank you all for being here.
Yeah, thank you to our panelists, hugely appreciated, and thank you all for attending. Hopefully this was educational for you. Please fill out the webinar evaluations. This is one of those things that helps people get promoted, so please fill that out.
Thanks, everybody.
Thank you all.